Hi everyone, welcome back to my videos. I like to do a tutorial on secants and tangents. Let's start off with some definitions. A secant line intersects a circle at 2 points. A tangent line intersects a circle at only 1 point, the point of tangency. So let's look at line 1. Line 1 intersects the circle at point A and point B. So it intersects the circle at 2 points. So line 1 is a secant line. Line 2 intersects this circle at only 1 point, point C, which is the point of tangency, and line 2 is a tangent line. Let's look at some postulates involving tangents and radii. Postulate 1, a radius of a circle is perpendicular to a tangent line at the point of tangency. Postulate 2, if a line is perpendicular to a radius at their intersection point, the line is a tangent. A few more definitions. A tangent segment joins a point outside of a circle with the point of tangency. A secant segment joins a point outside of a circle with the outermost intersection point of a circle. So if we look at segment CB, right, point C is a point outside the circle, right? And B, so point A is the innermost intersection point. By innermost, I mean the point that's closest to point C, right? And point B is going to be the outermost intersection point of the circle, right? So this whole segment CB is the secant segment, and you can extend this segment into a line, which is the secant line, right? Segment DE is a tangent segment, right? Joins a point outside the circle, point D, with point E, which is the point of tangency, right? Okay, so this is the main theorem for the section, the two tangents theorem. Given segment AB is a tangent segment, so I didn't write it down, but point B is going to be the point of tangency, right? Segment AC is a tangent segment, and C is going to be the point of tangency, and we're given this circle with center M, right? So we want to prove that segment BA is congruent to segment CA. So how are we going to do this? We'll write down our givens, and then I'm going to draw radius MB, I'm going to draw radius MC, and I'm going to draw segment AM. And I can do that because between 2 points a segment or line can be drawn, right? So segment MB is going to be perpendicular to segment AB because the radius is perpendicular to a tangent segment at the point of tangency. And I use statement 2 and statement 4 for this. And segment MC is perpendicular to segment AC. Again, same reasoning using statement 3 and statement 4. So I know the perpendicular segments meet at right angles, so angle MBA and angle MCA are right angles, right? So, using what I have in statement 5 and statement 6. So angle MBA is congruent to angle MCA because all right angles are congruent. We know that segment MB is congruent to segment MC because they're both radii of the same circle, and therefore they're congruent. Segment MA is congruent to itself by the reflexive property congruence. Since we're dealing with right triangles, right, we have right angles, so, you know, a triangle for right angle is a right triangle, so let's use the hypotenuse-like postulate. And using that, we get triangle BMA is congruent to triangle CMA, and therefore, reading off the congruences, you get segment BA is congruent to segment CA, which is what we wanted to prove. Okay, let's do a few problems. So we're given a circle of center M, a circle of center N, and points A, B, C, D are tangent points. Prove that segment AB is congruent to segment CD. So how are we going to do this? Well, we write down what we're given, and now we're going to pretend like this circle doesn't exist, right? And we just have these two tangent segments here, and then the circle with center M. Well, by the two tangents theorem, we know that segment AP is congruent to segment CP, so I'll write that down. Now let's pretend that circle M doesn't exist, right? So you just have, you know, circle of center N, and therefore we know that segment BP is congruent to segment DP. So since we know these two facts, we can subtract what we have in statement 5 from what we have in statement 4, and then we just substitute and we get segment AB is congruent to segment CD. Okay, so this is a more computational problem than the one we did before, but let's take a look at it. Segment, so we're given a circle of center O, a circle of center P, a circle of center R, and all three circles are tangent to each other. Not all three of them at the same point, but they're kind of pairwise tangent, right? So we're given the length of OP equals 12, we're given the length of OR equals 13, and we're given the length of PR is equal to 11, and we're given RP is radius of circle P, RO is the radius of circle O, and RR is the radius of circle R. So we want to find RO, and by finding RO, I mean find the value of the radius, right? So write down what we know, and then if we look here, so I'm going to call point A. I didn't include this, but I'm just going to do this for clarity. Point A is the point where circle of center P and circle of center O are tangent, right? So the distance from point A to point O, right, is the radius of the circle of center O, right? Because A is a point on the circle, and O is the center of the circle. So this radii is, this segment's a radii, right? And segment AP is also a radii, right? Because it connects point A to point on the circle with point P, which is the center of the other circle. So I'm going to use the betweenness property of segments and the fact that we have this tangent property to get length OP is equal to the radius of the circle of center O plus the radius of the circle with center P. And in this case, I'm using, these are measures, right? Because remember, radius can be a segment, can also be a measure, but in this case, I'm using it as a measure. And in the same way, we get length of PR is equal to length of radius P plus the length of radius R, right? And length of OR is equal to the length of radius RO plus the length of radius RR. So if I add these three quantities together, I get OP plus PR plus OR, and then you get 2 times RO plus 2 times RP plus 2 times RR, and OP plus OR plus PR, if you add these three quantities together, you get 36. So RO plus RP plus RR is equal to 36 divided by 2, 18. And if we look, RP plus RR here is actually equal to the length of PR, so I can just substitute that into what I have in this equation here in statement 9, and then doing some algebra, I get length of RO is equal to 18 minus length of PR, so RO is equal to 18 minus 11. The 11 comes from statement 2 where I substitute PR, and I get 7. Okay, we're given a circle of center B and a circle of center D and tangent points A and E. So I'm not stating it, but I'm going to save a little space, and we'll just say that BA is a radius, right? And DE is a radius of the circle. So we want to prove that length of CA divided by length of CE equals length of CB divided by length of CD. So write down what I know. And I know radius is perpendicular to the tangent line or segment at the common point of tangency. So segment BA is perpendicular to segment AE, right? Segment AE is a tangent segment, right? It joins, and point with point A is the point of tangency. Segment DE, so DE is also a radius, right, for this circle, and segment AE, the same segment, is also a tangent segment, except E is the point of tangency. It doesn't matter because we're dealing with these in 4 and 5 with this perpendicular kind of relationship. So angle BAC and angle DEC are both right angles because perpendicular segments made at right angles. Therefore, angle BAC is congruent to angle DEC because all right angles are congruent. angle ACB is congruent to angle ECD because these are vertical angles, right? They're kind of like, has like this hourglass kind of shape, right? And, you know, there's this vertex right here, the common point, right? C. So, okay, so we can use the angle-angle theorem for similar triangles to get triangle CAB is similar to triangle CED, and therefore length of CA divided by length of CE is equal to length of CB divided by length of CD. In similar triangles, the measure of corresponding sides are proportional. So this is going to be the last problem. I'm going to do my next video, and I'm going to include some challenging problems based off of this section, and maybe go over a little bit more detail on postulates and things like that. But I think we have enough here for video, so let's just go over this last problem. Given circle of center B and circle of center C, and we're given tangent points D and E, we want to prove that length of BD divided by length of CE is equal to length of AD divided by length of AE. So I write down what I know, and I can say that angle A, this angle here, is congruent to itself by the reflexive property congruence. We know a radius is perpendicular to a tangent line or segment at the point of tangency. Actually, this is at, let me just make a, sorry about that. So anyway, we know that segment BD is going to be perpendicular to segment AD, right? And segment CE is perpendicular to segment AE. So we know the angle BDA, this angle here, and angle CEA are right angles, right? Because perpendicular segments meet at right angles. So angle BDA is congruent to angle CEA because all right angles are congruent. I can use the angle-angle theorem with statement 4 and statement 8 to get angle ABD is similar to the triangle ABD is similar to triangle ACE. So therefore, in similar triangles, the measure of corresponding sides are proportional. So I can just read it off. Length of BD divided by length of CE equals length of AD divided by length of AE. So that's all I have for you tonight. I hope you enjoyed this video. I hope you got something out of it. And I will make some more videos on circles. So there's still a few more videos to come. So I want to thank you for watching my videos, and hope you learned something. And you know, I hope that these explanations are making sense. So I want to wish you guys a good night and hope to see you soon. All right, bye.